Okay, so last time we looked at the first example model, which was this one where the basis was just one single vector, one, right? And we had two sectors, which were therefore 1 and 1 plus 1, which is the NS. And we started using these like model building formulae, like the mass formula and the GSO projection formula to derive the spectrum, the Hilbert space of states. And we found first, so what did we find? So the one sector gives massive states, so we didn't really need to worry about it. The NS sector can give massless states, and it can also give a tachyon. So we found that there was a tachyon, which is where if we have this NS vacuum, so this is the combined vacuum of all the fermions being NS, so that you have 8 on the left, 8 NS vacua for the space-time fermion, and then 16 on the anti-holomorphic side for the gauge. And then we said that we can act with one of these gauge fermions. I can't remember if I used what notation I used, but let's call it phi bar. These complex fermions, let's say on the right, or the anti-holomorphic side. Okay, so there was these six.
Ben, would you mind using the board that's the right side of the divide?
Yeah. Is it all right if I just finish the summary and then I'll leave it up?
Okay, yeah, that's perfect.
And I'll try and write for the rest of the lecture here.
Yeah, that's perfect. Thank you.
Okay. So we found that there are 16 tachyons. These are tachyons because the mass on the left is, or the mass on the holomorphic side is, remember the mass formulae. So on the holomorphic side, we had -1/2, which is this from the fact that we have a supersymmetry on the holomorphic side. This means we get -1/2 rather than on the anti-holomorphic side we get -1. So this is like for superconformal, and this is a conformal vacuum energy. And then we add on the Ramond contribution, which was like alpha dot alpha on the holomorphic side over 8. And the same thing on the anti-holomorphic side. And then we add on the oscillator contribution. And so for this tachyon, we found that on the holomorphic side, this is 0, so you just have -1/2, so it's negative. And on the anti-holomorphic side, this thing contributes, the oscillator contribution is 1/2. So you get -1 plus 1/2, which is -1/2, so it's level matched. So you have -1/2, -1/2, but it's negative, so it's a physical because it's matched, and it's negative, which means it corresponds to a tachyon, which is essentially means that your theory is sort of inconsistent. It means you haven't formulated the correct vacuum of the theory. There's a sort of fundamental instability in the theory. The idea is if you have a tachyon, then any sort of, you usually have to formulate a physical theory at a stable point, which means a point where, like, let's say at the bottom of the hill, because then things can be said to be stable, they sit in the minimum of a potential. But if you have a tachyon, that means the theory moves, and it's like a downhill or an uphill or something. This means that the way we formulated this theory with this basis is a sort of fundamental, like, inconsistency in the theory. So you don't want tachyons. So we're going to see why we now introduce another basis vector that will help us get rid of them. Okay, so I'm going to rub these out. I'm going to hopefully today just assume that you remember these mass formulae and the GSO projections and the ABK rules for the basis vectors and the GSO phases. But I'll tell you when I'm using them and how I'm using them. Okay, so what else did we find from this model? So we had, in addition to these tachyons, another point about a tachyon, these states were if you try to use a GSO projection, so in this model, the only GSO projection there is the basis vector 1. So if you do the GSO projection with respect to 1, then this state remains in the spectrum. And last time I got, I'll just clear up, I got confused with the GSO phase for the NS and 1 sector. So I'll just explain that in a second. But first, just for the other, so for the massless states in the NS sector, you have to act with either two like complex fermions on the anti-holomorphic side and one holomorphic oscillator as well, in order to make it mass equals 0 from the mass formula. So that could be done in a couple of ways. We could also act with a bosonic operator on the anti-holomorphic side, because a bosonic operator contributes a full +1 to the mass formula. So we had two possibilities at the massless level. So maybe I'll just write here. So these were when the mass was -1/2. The other states, so we had, if we act with psi mu, that contributes 1/2 on the anti-holomorphic side, sorry, on the holomorphic side. So that pumps the holomorphic mass up to 0. And then we act with either a bosonic operator, which the bosonic operator is just the derivative of x mu, or x nu, because we use that mu here. And that acts on the NS vacuum. This is now massless, because this is like contributes 1/2. Sometimes we write the contribution here, 1/2 and 1. Okay. And the other possibility is to act with psi mu, and then instead of one bosonic, we could act with two fermionic, anti-holomorphic. And let's call this A or I. Sorry, I used I before. So one I and then one J. Oh yeah, one note is that when I write this, I could rewrite this equation in the following way, where we make it clear that we're splitting the holomorphic and anti-holomorphic vacuum in two. So, for example, this here could be rewritten as psi mu acting on the left, or the holomorphic vacuum, and then tensor product, because you know, like in quantum mechanics, you combine states in Hilbert space by tensor producting. So this would be like this. So you're just splitting the left and the right, or the holomorphic and anti-holomorphic. But I'll tend to just use this notation where you just you kind of remember which is which side is which. Okay, so what did these states represent? So how illegible is it on this side for E?
Well, it's perfect. Like this side is visible. And let's consider the right one a little big.
Okay.
Yeah.
Well, yeah, I'll just try and leave this up in a second. So we said last time this is essentially a two tensor because there's two space-time indices. And so in order to say what states these are, you have to look at the basically irreducible representations of a two tensor under the Poincare group. And we said that this is like there's a symmetric part, an anti-symmetric part when you decompose the matrices, and then a trace part. And this corresponds to a graviton, which is the symmetric trace, sorry, the symmetric part, then the anti-symmetric tensor and the dilaton, G, B, and phi. So you could write this, yeah, that's fine. Okay. And the dilaton is just a scalar field corresponding to the trace part. And then these states here were associated to gauge bosons. So we see there's one space-time index. So there's one space-time index, which means this corresponds to a vector. So anything, you know, with one space-time index is like something that's going to transform as a vector. And then these parts here, I and j, these relate to the 16, you know, the 16, the C equals 16. If you want from the conformal field theory perspective, there's a conformal field theory, the gauge part, which is like a 16 dimensional gauge space. And these, so these will give essentially representations of the gauge group generated by these 5 R's, these gauge fermions. And if you do I equals j, so if these two oscillators, these two fermionic oscillators are the same, what we call these are like the diagonal part of the gauge group. So they are like what we call the cartan. So this is called the cartan. The cartan of the gauge group. And so there's 16 of these, remember? So there's 16. So you could say this is 16 cartan generators. And then if you look at the other part, which we just have to take, let's say I greater than j or j greater than I, one or the other. These other ones are the non-diagonal part. And together, so I think this is just called like, yeah, non-diagonal. Okay. And together, I was hoping to fit this onto one bit. So together, these states, psi mu, phi bar I, phi bar j, these correspond to the adjoint representation of SO, and then because there's 16 complex fermions, this is 2 times 16, so it's 32. So there are 16, basically the adjoint representation is essentially defined as the sort of natural embedding of these gauge generators, where you've got cartan, like the diagonal part, which is where these are the same. So there are 16 of those. And then basically the other, like the upper triangle part, let's say, where I is greater than j. And so there would be n times n plus 1 over, n times n minus 1 divided by 2 of those. And together they span the adjoint, which is just a natural matrix representation of the gauge group SO2D, and D is 16 here, so it's SO32. So one thing to note is what we'll see is that if you did GSO projections, you could you could restrict which I and J's you have. So there could be groups of these two that split. Basically, you split them up. They can't. Some of them can't go together. You can't have some J's with some I's, but you always have the diagonal part, the Cartan part. So the Cartan part, this bit I equals J. There's no GSO projection which will project these. Also the Cartan part you can just relate to the fact that so the Cartan part, if you just write like this is like a U1 current. So the Cartan part is essentially the isomorphic to the 16 U1 currents generated by each complex fermion. And usually when we can essentially formulate the gauge groups in terms of currents as the current algebra. So, okay. So that's really the main parts I think I wanted to recall from last time about this model with one basis vector. Just get rid of it. So what we want to do now is add a basis vector that makes this model better. And what better means is that we get rid of the tachyon, and we're also going to try and get supersymmetry, space-time supersymmetry. Okay, so now let's do a new model. So next model. New model. 1. So we're going to always start with the vector 1. Okay. And then we're going to add S. And S is the following. S is just the vector where phi mu is periodic and the gauge degrees of freedom are anti-periodic, which is, we've also written it as 1 and then 0 like that with the boundary conditions.
So is it 0 to the, I cannot say, can you read it out loud?
That's a 16.
Okay, 0 to the 16, okay.
So they're for the 16 gauge fermions, complex fermion. And it's 8, remember, because this is 10-dimensional space, but in the light cone gauge.
Okay, I remember that.
Okay. So now we can say, so yeah, so let's try and be systematic about when we look at a model. So what do we also need to specify? The GSO phases. So the GSO phases are the other like unknown ingredient for a model, right? So now we have a slightly less trivial set of GSOs. We have C1. And yeah, I didn't clarify that point about the GSO phase between 1 and NS from last time. I'll do that. That'll probably come up when we do this the same thing for this model. So I'll explain it then. Okay, so C11, C1S. And actually, C1S, if you look at the GSO rules, this is related to CS1, because you can, if you do the GSO rule where you flip the two. So this is going to be CS1, and then you've got an exponential of I pi this dot this. So you should have 8 on the left on the holomorphic from here. So this should be plus. So these two are equal. And using the other GSO rule for the diagonal, you can also relate this to CSS. And there's a minus E I pi over 4 dot, and overall that should also be plus. So they're all the same. You can just check that if you're not sure. Look back at the GSO phase rules. Okay, so there's actually only two independent phases. Okay. And then you can determine also the NS projection, the ones with NS, because NS is a combination of 1 plus 1, basically. Okay, right, and then we can write down the sectors, right? So alpha. So alpha for this now is slightly less trivial than before, where we only had 2 sectors. Now we've got 1, we've got NS. So 1 plus 1. But then we've also got S. We've also got 1 plus S. And I think that's it. Yeah. Does that make sense? So let's just, we have to now do this one by one. So we have 4 parts. So 1, I'll call this 1, I'll call this 2, call this 3, call this 4. Right. Let's say 1. So 1 is the sector 1. And that's have, again, the math formula tells us that this is, so the sector 1 was massive, right? So in particular, like the mass is greater than 0. So it's massive. So we don't need to worry about the 1 sector. And we can also comment that, let's look at 1 plus S. Is 1 plus S, and let's just see 1 plus S is, so the sign mu is 1 plus 1, so that's 0. And then the gauge fermions are periodic, so 1 and the 16. And this is going to be on the, so if we look at the, so 1 plus S, so if we look at the anti-holomorphic mass, this is going to be minus 1 plus 16 over 8. So it's greater than 0. So if you want a level match state, it's going to be massive. So 4 also is massive, but we don't need to worry about it. So we really need to just worry about 2 and 3, the NS and the S sector. Okay. Is that all right? Yeah. So we will just do, so the NS is going to be very similar to what we did in the 1 model, just 1 basis vector, but you've got the GSO projection with S now to act on the sector. So let's do the NS and S. Okay, so NS. So 2. The NS, similar to before, we get the same kind of states at the massless level. But let's say first, let's look at the tachyon. So last time we said we had a tachyonic state like this. And before, this was just in the spectrum because the only projection we had was 1, and 1 doesn't project this state. In particular, let's do that again because we'll see what I did last time and explain it with the GSO phase between 1 and NS. So the GSO projections on this tachyon, if we do 1, then we have e to the I pi 1 of NS so remember what I was getting confused about last time was that you've also got to act on the oscillator. So this would be like 1 boundary condition of this dotted with the fermion number of that oscillator plus the boundary conditions of all the fermions in the NS, which is just 0 basically, dotted with the fermion number of NS or aperiodic fermions. And this bit's clearly 0, but this bit here from the oscillator, this gives you, so this is 1, because this is the boundary condition of this in the vector 1. And 1, you know, everything's periodic, so this is periodic, so this is 1. The fermion number of a periodic fermion, that gives you -1 from the definition of the fermion operator. So this bit here is -1. It's 1 times -1. So overall, this gives you a minus sign in the exponential, so e to the minus I pi. So that's the left of the left-hand side of the GSO projection, and then that should be equal to delta of NS, which is +1, multiplied by the GSO phase of NS with 1. And I was right last time how, sorry. So I was right last time. This phase, if you do it, this is 1 + 1, and you rearrange it using the rules, and you get -1. So this phase is -1. This is +1. So it's the spin statistics operator of NS, which is +1 because the boundary conditions are basically because this is bosonic. It's got no. It's the psi mu is aperiodic in NS. And then this, we did the rules. It was correct. What I did last time, this is -1. But we had to remember that this part here, the dot product, has the oscillator contribution in it. So this, I think what I said last time was that this part should be 0 because the boundary conditions for NS is 0. But there's also the bit from the oscillator in the tachyonic, this sector, this state. So this -1 and this -1 match. So that means that the tachyon survives. So tachyons, or the 16 tachyons, survive. And that's why the one model had tachyons in it. Okay. But now let's do the projection with S. And hopefully the whole point of this S is that it's going to allow us to project these tachyonic states. So we'll do the same thing, so we can kind of be very presumptuous and say we're going to have something very similar. So now we're going to project with S. Okay. So the S projection, we've now got the left-hand side of the GSO projection, where we do S, boundary condition on the oscillator, dotted with the fermion number of the oscillator, plus the boundary condition of the NS fermions, dotted with the fermion number of these NS fermions, acting on the vacuum is equal to the spin statistics index of NS times, and now we change the phase to be NS with S. Okay, and then what we see is so here S acting on this is 0, right? Because S only has periodic boundary conditions for psi mu, and it has aperiodic for phi bar. Yeah. So now this bit for the oscillator, this is 0, and this is 0, but this phase here, you can write it out if you want. So this is C1 plus 1 of S, and then you can apply the ABK rules, but you will find that that equals -1 as well. Okay. So you've got the same thing here. It's -1. This is +1 still. That didn't change. So you've got -1 here, but then because this boundary condition is different for S than 1, this part is 0, this part is 0. So you've actually got +1 on this side because you've got e to the I pi of 0, which is +1. So this is +1, but this side is -1. So this is the tachyons. So the two sides don't match. So that means that the GSO projection has projected this these tachyonic states. Okay. Right, that's good. And then now what we can do is look at the massless states from NS and do the same thing with the projections. But we've got this is an important result. Like this is one of the reasons why you need what we'll see as well in the massless states is we get supersymmetry basically, and that this S gives us supersymmetry, and by giving us supersymmetry, it projects the tachyons. So the reason you have supersymmetry and string theory together is because to formulate string theories, particularly in 10 dimensions, that don't have tachyons, you generally need supersymmetry. But we will see that that's not entirely true a bit later. Okay. So now, yeah, let's do the massless states. Okay, so the massless states, we had the holomorphic oscillator with the, so let's start with this one, the bosonic operator. Okay, if we do the GSO projection with 1, we already did this last time. It's exactly the same as the 1 model. And you should find you've got 1 acting on this, dotted with the fermion number of psi mu, plus 1 acting on delta x mu, dotted with the fermion number of delta x mu, and then plus 1 acting on ns dot the fermion number of ns. These two parts are going to be 0. So this is 0, this is 0 as well, like fermion number of a bosonic operator. It's going to be 0, and then this part is 0 because, I mean, this is the boundary conditions of zeros are zeros, right? So this part and this part are 0. Okay. And then this part gives you -1, a bit like before, because the boundary condition of psi mu in the vector 1 is 1, and the fermion number of psi mu is -1. Then on this side, you've again got the same thing as before. You've got +1 for the space-time index, and then the GSO phase is -1. So this survives. Okay. So you've got these, so that the whole point is that these states have to survive because they've got the graviton in it. And you need them to survive because one of the main points of string theory is that you do get the graviton, the symmetric part of this, to tensor. Okay. So if there was a projection in this of this state, then there would be something wrong with the model, with string theory, really. And then we can do the GSO projection with S. So instead of 1s, we get S's. And everything is exactly the same if you look at it, right? Because the boundary condition of psi mu in S is 1. The fermion number is -1. This is 0 again. This is 0 again. For the same reasons. On this side, you have this -1 from the GSO phase. So you've got -1, -1, so that it survives. And that's good because you don't want to project these because they have these important states, the graviton, mainly the graviton, and then you always get this anti-symmetric part and the trace part of the scalar dilaton. So this is kind of why these GB5 this is why we usually call these three the model. These are model independent. You can't really cook up a vector that will project them. Okay, so they are always there, regardless of the model. Is it a bit dark? Can you see all right? Yeah. Okay. And then, so that was the bosonic operator bit. So now let's do the gauge bosons part. Okay, so the NS, so now let's do psi mu, and then phi bar I, phi bar J. Okay. And then we do the GSO projection, let's stay with 1. And here now we've got 1 plus the first oscillator. And then we also should have, so let me try and rewrite this bit. So now you've got the 2 fermionic oscillators. So 1 with phi bar I, F with phi bar J, sorry, I, and then the same thing. I'm going to just put, I'm going to write it as a sum to save space. sum where A is ij. Yeah, and then plus 1 of 0 plus f of 0. So this bit's clearly 0 again. And then again, you've got GSO phase with 1 and S with 1. So you've got minus 1 on that side again. And then here we now have 3 oscillator bits. Okay. So we've got the oscillator bit for this, this, and this. This one we said is -1. Nothing's changed. This is still -1. This one is again going to be -1 because it's the same thing. This is periodic. This is -1 because it's fermionic. And then you've got 2 of them, so it's -1, -1. Okay. So overall, you've got 3 -1s, which is -1 overall, or still gives you a, when you take the exponential, you still get -1. So the 2 sides match. You get -1, -1. So so these vectors, or these vector bosons, they, for the gauge group, they survive the 1 projection. Okay. So let's see what happens with the S projection. We're going to do this very quickly. Maybe you can just quickly try and work out what's going to happen with the S projection. Farid, Eman, or Alonso, do you want to say? So what's going to happen?
Yeah, I'm just okay. So it's going to be 0.
So you've again got the 3. So what's going to happen here? So you've got 3 oscillator parts. So what's this part, the first part? So we get -1. Yeah.
Minus.
Yeah, can you see that? So
Yes, I can see. So it's going to -1, right?
yeah, this bit's -1, and these are
Okay. The thing.
the bits with the fermionic oscillators are
1, right?
no. So what's S of phi bar?
Is 0.
0, yeah, good.
Yeah.
So these are 0. So
Oh, okay. Oh, okay. Yeah, I see now.
so you got
Yeah, it's
0.
0 and 0.
But again, overall, this is -1 here, so you have e to the I pi minus so it's -1 overall. So the 2 sides match, so the vector bosons survive. So we still have the SO32, basically. So the SO32 adjoint, or whatever, the SO32 that we got from this one model, it survives in the S model. Okay, so that's all. The NS sector is therefore completely the same. There's no difference. The GSO projection from S didn't do anything extra in that sector. Okay, now let's do S. I'm not sure exactly what I need yet, so let's work this out. I think soon I'm going to make it a bit more collaborative. So if I write down the model, hopefully you're used to the rules and then you'll just be able to do it yourself. And I might give you some homework next week to do a model yourselves by adding an extra few basis vectors.
Yeah, that's all right.
Yeah, and then if you have a go at doing everything, and then if you get stuck, you can ask. But
Yeah.
let's finish this model, and then I think we should be in a position I can maybe give you a model to do, maybe even today. Okay, so GSO projections for, so we're going to do the S sector now. So the S sector, will introduce some new components to what we've done so far. So the S sector, remember, this is the S sector. You've got 8 Ramond fermions. So let's just write here the masses on the left and right, the holomorphic and anti-holomorphic. So this is -1/2 plus so this is going to have to be 1 to make it massless. This bit is actually, yeah, so 8/8. So this is, no, wait, so this should be 4, right? Because it's complex. So really, sorry, I got confused there. So this we can, if we write 8, that's the 8 space-time transverse fermionic coordinates. But those should be complexified into 4. Or we can think of this as 8 real, but then it's half. Yeah, so 8 times 1/2 to get 4. So really, these sine mu's, you can think of them as 8 real degrees of freedom, or 4 complex. So that gives us the massless state. So hence we can get massless states that are level matched with an anti-holomorphic oscillator equals 1.
Can I ask a question?
Yeah.
If I wanted an oscillator, do I always have to use a complex one or a real one? Or
yeah, so you can use a real one.
And the counting is like 1/2 of each, 1/2 for the real and 1/2 for the complex.
No. So the frequencies are the same, but if you have a single real oscillator instead of a single complex oscillator, then what it means is that it's like this thing, you realize different gauge groups, because when you make the correspondence between a real oscillator to a, like, you can, for example, think of it as like a bosonization. If you have a complex fermion, can be easily written as like I del X or whatever, as in a bosonic language. But if you have a real one, then basically the normalization, there's a different normalization, which if you look at if you analyze the like current algebra and the Catch-Moody algebra, like, or operator product expansions, then it will give you a different Catch-Moody level usually. So, or it can be a non-simply laced group, because it changes the roots. So you have to have basically the different normalization when you try and bosonize it can be counteracted by having a different length root, which is like having because usually in like an SO2n, the roots of the algebra are like root 2, and then that coincides with the case where you have complex fermions, basically. And then with real fermions, you can't say that the roots are root 2, because then the normalization doesn't work when you do do the bosonization. Well, that's at least my understanding of how to explain it. But in all the models we look at, we tend to try and form, because we tend to try and form the model so that any real fermion it is paired up naturally with another real fermion to make a complex fermion. So that all the representations tend to be SO2n. But it does occasionally happen that you can get, when we look at 4D models, for example, you can sometimes get like SO2n plus 1, so non-simply based groups, through like having a real oscillator. But yeah, that is a kind of confusing thing sometimes.
Okay. So like, for example, NA equal 1, I could use two complex or two real fermions.
Yeah. Yeah, the frequency is the same. So the frequency is like this. And it doesn't depend on the only difference is that obviously with the real you don't have we need to always remember that if you have a complex one, you can always take the complex conjugate and act on it, but in the real case you don't have that. So yeah, that's the main difference is that yeah, you can't have, because every complex oscillator really has two parts, and I kind of ignored that probably when I was talking about the, like here, these can always be NF complex conjugate as well. So that's, and you actually, if you wanted to do the full counting of how many states there are here, you should really count all the complex conjugate with the non-complex conjugate possibilities, and that will give you the full number, which for like the full dimension of the representation. So here we said that we had the adjoint of SO32, and the adjoint of SO32 actually has dimension 496, and 496 comes from, you have to get that by taking all the possibilities of these I and J's with the complex conjugates, and then it works out if you count everything up, but otherwise it doesn't. Yeah, but we're always just thinking about complex fermions, which makes everything easier. And I'm sorry if anything I said was wrong. It's possible, but I think it's something to do with that normalization in the bosonize. When you write the fermion as e to the I of x or something, and you check the OPs, the operator product expansions in the conformal field theory, there's a different normalization factor in which is usually related to the Catch-Moody, like k, and then that k is related to like the lengths of roots in the Lie algebra or the level of the Catch-Moody algebra, and then you have to go. So you have to kind of go into the representation theory or whatever to understand it. I think the Lie algebra to understand it. Yeah. Okay, so now S. So S, what we said here was we've got minus half plus a half, because you have four complex space-time fermions. And then here you have -1, and then you have to add on an oscillator. So again, we have two choices for that oscillator, right? Because we can either choose dx acting on S, because this contributes 1. So this would be like NA is equal to 1. Or we can choose two fermionic operators. So we can also have these okay, so there's two possibilities there. Let's call this 1 and 2. and do the S projection on one. So the S projection on one is going to be S acting on the bosonic operator, which should be 0, and then I think before I maybe forgot the bar on the X in a couple of times. Like here, this is X bar, because it's from the anti-holomorphic part. And then plus S acting on S. So the boundary conditions of S, which you already wrote here, plus multiplied by the fermion number of S. So what this really means is, you're going through all the fermions and checking the boundary condition in sector S and multiplying it by the fermion number of that fermion. So really, this is like a product over all the fermions in the sector S. But we just write it like this, dot product. So the dot product here kind of takes account of that. Okay. Then we act on the S vacuum, which is so the S vacuum, remember, corresponds to, so S vacuum is going to be a Ramond vacuum, which is like this spin up and down, a Ramond vacuum to the power of 4, so 1 for each complex fermion, these psi mu's, tensored with the NS vacuum for the 16 gauge fermions. Right? And then on the other side, we have delta, delta of S, C of S, and then if we project with S, I don't know why I'm projecting with S before 1, but it doesn't matter. So we're just doing the S projection here. Okay, so S projection, we said this was 0. So this is all 0. And then this thing here, this is a key thing. So you have to think, like I said, you really, this dot product is going through all the fermions. You've got 4 Ramond fermions, so 4 periodic fermions, and 16 aperiodic. The aperiodic ones, so the gauge fermions, these are just going to give you 0 because the boundary condition is 0. So really this bit is the same as the boundary condition for we just have to look at these 4, the space-time complex fermions. So this bit here is like essentially S of psi mu dotted with F of psi mu. So the other part 0. And obviously this is 1. So this is 1 because that's the boundary condition of psi mu in S. Then the fermion number is this is good because it makes me review some things that I forgot. So I think actually
It should be +1 for the minus.
Yeah, but I think the way I'm just thinking that how does this work? Because in
No, you have to do the.
but don't they all have the same vacuum? All the directions should have the same vacuum.
No, there you have to distinguish between the total number of minuses.
Yeah. So I mean, so I know this. So if you act with, remember, if you act with F on the minus, you get -1. But if you act with F on the plus, you get 0. Okay. But I think from the 10-dimensional, like in the 10-dimensional model, what you have to say is that this is really either plus or minus. It's not the combinations only arise when you look at lower dimensional models. So it's either plus or minus with the degeneracy, because I think all the vacuum, all the Ramons, yeah, the vacuum for each direction in this space-time fermion should be the same. I think, but I hadn't really remembered that until now, and I need to work.
How many states we get comparing with the supersymmetric?
So what as well? So because what happens here is this is only one state. But if you split the vacuum, like if this could be like plus minus minus plus or minus minus plus plus or something, then you'd have lots of combinations, and that would mean there was more states. But with this, you have just one state, just a state plus 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 or minus 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 minus. So it's just one state for that, and I think that's how you're supposed to, how it's done, and that's because the space-time fermions in 10D, they all should have the same boundary condition, and therefore and the same vacuum. So sorry, they all should be Ramons, but they should all be plus or minus. And what this projection is going to do is fix it to be one or the other.
Sorry, Ben. So you said it's like there's like a plus, like 4 plus states, and it equates to 1.
Yeah. So there's so in theory, like this.
Yeah.
And we'll see this in other examples.
Yeah.
But usually, like if you had 4 periodic fermions,
yeah,
this could be rewritten as like plus minus plus minus plus minus plus minus.
Yeah.
Right, and that's in general. There's 2 to the 4 combinations there. 6 combinations.
Yeah.
But what I'm saying is that we really only have plus 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 or minus 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 minus. Because the vacuum should be the same for the space-time fermions in these 10D models.
Okay. Okay. So,
Even
but like
in 4D, that's true, right? Because we have 2 directions, sine mu 0 and 1, or whatever. So two directions, 2 light cone directions in 4 dimensions, and we just leave the vacuum as plus or minus. So the space-time fermion should have the same boundary condition, the same vacuum. So so there's only 2 choices: this one or this one.
So do we get like 2 projections, like so like the Fermi number for like plus 4 pluses, a Fermi number for minus, like
yeah, exactly. So this is what I think.
Yeah.
No, so I think what you do actually is you basically just count this as one vacuum.
Okay.
So this is actually just one vacuum, either plus or minus.
Yeah.
Yeah. So this isn't like a product. Yeah. So yeah, maybe what I was saying before, I wasn't thinking correctly. It's mainly because in 4 dimensions, I'm more used to 4 dimensions, and then it's a bit easier. Like it's sort of already taken care of. But yeah, the vacuum should be either plus or minus for the whole space-time fermion. So this is either plus or minus, so it's either 0 or minus 1. So we can write this as 0 or minus 1. Okay, we don't know yet which one it is.
But when do you do the Fermi number only on the side and on the chi?
So the chi is because we're in 10 dimensions.
Okay.
So remember, the chi's are the the compact superpartners for the compact directions, the bosonic compact directions. But in 10 dimensions, we haven't got any compact space, right? So this 1 to the 4 is just psi mu. That's it. But the mu runs from 1 to 8 if it's real, and then 1 to 4 if it's compact.
But then you can like psi times 4.
No, so that's what I'm saying is like the vacuum for psi mu is grouped because they're the space-time fermion. It should be either plus or minus, the whole thing.
Either plus.
So the whole thing transforms as a single spinner in space-time. Because it's like the difference has been like a world sheet field, which chi is a world sheet field, right? It exists on the world sheet, it doesn't have a space-time index.
Yeah.
So it has each chi has an individual Ramond vacuum.
Okay.
But in psi has a space-time index. So in space-time, it corresponds to a single spinner representation. It's plus or minus. That's the correct way to think of it. I just hadn't thought about it for a while. But yeah, so when we look at 4-dimensional models, we'll see how it's a bit different. But it's basically the difference between the space-time and the world sheet.
So now you have to think of those 4 as 1.
Mm-hmm.
Okay.
Yeah, because so I mean, for example, here, remember, like when we were looking at these states, we had psi mu and dx mu, and we think about these as forming representations in space-time. So because we look at the mu's and the nu's, and we know that they're space-time fields. So the representations are the representations of the Poincare group in 10 dimensions. But when we looked at this part, the I and J, we know that the I and J, these are world sheet fields. They relate to the gauge part of the theory, in fact. And so we think of these as having essentially world sheet descriptions. And so they form representations on the world sheet and not in space-time. It's a bit confusing. Yeah, that's that. So let's just finish this. So it's what's half? Okay. Are we okay to go for 5 more minutes? So,
Yeah, I'm totally fine.
let's try and finish this S1S model. So what I'm saying is that this is this S of psi mu, that's +1. The fermion number of psi mu is either 0 or -1. It's a single spinner in space-time. So it doesn't have, we don't have these 4 components. So basically this is wrong way to think about it. This is a single space-time spinner. Okay. So this is 0 or -1, and we don't know yet. The GSO projection is going to tell us which one it is. So on this side, we've got the space-time index of S. This time, the space-time index of S is -1 because this is a fermion, basically, because it has psi mu in it. Then CSS. So CSS is so we know that CSS equals CS1 because we said that before, and we know that equals C1S. But this is undetermined. We haven't chosen it yet. We have, for a model, we have to choose whether this is plus or -1. Basically, what we see here is that if we choose +1, so if this phase is +1, which corresponds to choosing this phase as +1, then on this side, so this side is going to be -1 because it's -1 + 1. So with this side we have -1. That means that this psi mu should be a minus, like a spin down or whatever in its spinner vacuum. If however this GSO phase is -1, i.e. this is -1, then you've got +1 on this side, which means that this is going to be plus. So what we see is that the conclusion here is that if CSS, which let's actually say C1S because that's the independent one. So if we do C1S, C1S is equal to +1 or -1. If it's +1, then we get this chirality. The vacuum for psi mu is minus, and if we get -1 for this GSO phase, we get plus. Okay. So essentially, this GSO phase just determines the chirality of this state. Okay. Right. So. And one thing we haven't said is, yet is what does this state represent? So we've got a space-time index here, and this thing is a plus or minus space-time spinner. Okay. So what we have essentially is a vector and a spinner together. And that actually corresponds to, so you can think of the vectors like adding 1, space-time statistics, and then the spinner is like a half. So together this is like a 3/2 space-time representation. Okay, and 3/2. So that's spin. The spin of this is 3/2. So that is what we call the gravitino, and it's the superpartner. So in the language of supersymmetry, it's the superpartner of the gravitons. Basically graviton because it's the superpartner of this state. So this state had basically spin equals 2. Mu and nu were both acting as vector operators. And if you transform, if you have this this spinner here for psi mu, then you get a half representation, and it makes this a spin half, 3/2. A spin 2 and a spin 3/2 form a single representation in supersymmetry, and you sort of put them together into a single representation, super representation, with the graviton and the gravitino as the two, the bosonic and the fermionic parts. So this is why we now say that. So all this projection does is we either have plus if we have this choice of phase. This one -1 or minus if we choose +1, but we still have this spinner. So it's one of the two chiralities. So either way, we're going to get supersymmetry. And actually, this is n equals 1 supersymmetry because there's a single graviton. Sorry, a single gravitino associated to the plus or the minus, depending on this GSO phase. So what the introduction of S has done is it projected the tachyon, but it's also given us this state here, which is associated to a gravitino, which is it gives us supersymmetry, or n equals 1 supersymmetry. And then really we need to do this one. So we looked at this kind of state before, but without the with the sign mu. This maybe I can just do this. So if you have this state here, you have to do the 1 projection and the S projection on this thing. If you do that, if you do the S projection, you can kind of see that these are going to be 0 because they're aperiodic in S in the GSO projection. On the other side, you're going to get plus or minus 1 depending on this GSO phase. So again, S isn't going to project these out. The gauge bosons, or these are actually. You can think of these as being spin because of this. Again, we have the S vacuum, which is the spinner of sign mu. This is spin half. These are going to be the super partners, so the fermionic partners of these guys. So these were the spin 1 vector gauge bosons, the ones where you have sign mu, which are from the NS sector. These are the partners of those, but with spin 1/2, so the fermionic super partners, where you've just not got the sign mu operating on them. And they're called, so the super partners of gauge bosons are called gauginos. So they're called the gauginos of the SO32 that is generated by these gauge bosons. The S, as I said, the S projection, if you do the S projection, it doesn't project them out, they're always there. If you do the 1 projection, it's basically the same as what we've done before. And that's the main point of this model. I think that's all I want to say on it, and you can check the details yourself about like doing the GSO projections on these, because I also didn't do the 1 projection on this, but the 1 projection on this is the same, gives you basically the same condition as this, because you just have this phase C1s, and you'll again, the choice of this C1s will just choose whether you have the plus or minus spinner for sign mu. So it gives you the same restriction. So that's the S model, the 1S model. There's one other thing I wanted to say about it, but we can do that next time. Okay. And then I think we're done, unless there's any questions from you.
I don't have any. Thank you.
Is that all right?
Yeah.
Yeah, I could. Do you want me to give you some homework?
I would love to.
Yeah. Okay, so the homework is, let's say, I want you to try and look at a model with 1 S, and let's call it chi. Sorry, whatever that's called, zeta. Let's call it zeta. And zeta is going to be, let's say, 1. So it's going to be these 8 complex fermions from the gauge side, which is also the same as writing more 0 because it's 4. So these are on the holomorphic side, and then so we've got 8 periodic and 8 anti-periodic. So I've just introduced this basis vector where essentially we're splitting the boundary condition in the 16 complex fermions into 2 groups of 8. Okay, so one thing you can do first is do the following. So check the ABK rules. So you can check that this is modular invariant, and then derive the matplet state. So you can also like write down the sectors, the alpha equals what, and then determine the massless ones. You can also just check there's no tachyons if you want, but it's the same as the 1S model. And yeah, just interpret the state. Okay. So interpret, like, you get very similar states, for example, in the NS vector, but what's changed by introducing this? So so interpret the matter state and do the GSO projections. And then interpret the states. Okay, is that all right for you?
Yeah, that's all right. Thank you.
You got it?
Yeah, thank you.
Okay. Right, I'll see you next. We could probably do the same time next week.
I'm totally okay.
Okay, right.
Yeah, well, thank you.
Thanks.
Take care. Bye.